Well, we've got a huge crowd today, and I'm very excited that you've all decided to come along and listen to us. What we're going to talk about is world leading edge technology, which actually allows us to predict floods and actually manage those floods, particularly using networks of upstream retention ponds. It is exciting. We get very excited about the whole world of systems. So we want to talk today about not just a bit of work that we've done, but actually about the power of systems and how they're going to transform the world. That's all. So let me crack on with this. Now, over the last year, we undertook a research project which was partly funded by the Institution of Civil Engineers. Thank you very much. And this work was undertaken with Global Environmental Engineers, WSP. Now, we've been working together for the last 3 or 4 years on a number of research projects, and this one fits in nicely with the whole idea of smart thinking, smart systems. Now we go back to work that we did right back in 2013, where we actually looked at some upstream retention ponds here. I won't go into this too much, but it basically proved the principle. On the left, without upstream flood retention. On the right, you can see the ponds A and B there. This is near Nuneaton. And what we showed is that actually by using networked upstream retention ponds, one was built against a railway line, another one was dug out here. You achieve a number of things. And we were very excited about this because we were working from hypothetics and we actually proved the case. Firstly, you actually end up with much more effective downstream flood control. So we were reaching our objectives for the flood levels there. Secondly, the actual amount of retention ponds that you need is smaller than if you are having a manual system, because effectively what you're doing is continually shifting around small amounts of water just in time in order to make the most of the capacity within the available system. And thirdly, and importantly, it means that you can actually drain down a system ready for the next storm to come in. How many times has there been one storm which is then followed up by something else and you actually get multiple flooding events? So this is increasingly important. Now I just want to show you a little bit of theory. I don't know how many of you get excited about flood hydrographs. I've done a little video, a little animation on this, which is available on YouTube and very well worth seeing. But I just wanted to point out a couple of little points on water theory. And the key to all of this sort of systems management is about how you manage surface water and how you manage it just in time so that you're avoiding the red line at the top. It isn't rocket science, but it's quite neat when you see it. What we don't show on here is what is actually happening to the reservoir levels which have been set upstream to release water when it's needed and actually capture water. And really what we've done with our system is to try and fiddle around with as small an amount of water as possible in order to just stop those peak flows from causing the flooding. We don't need to do anything more than that. And so the volume of water we're shifting around is shown at the top here. This is a time line along the bottom here, the number of hours, and these are flow rates meter cubed per second. And we're trying to show what happens with the rainfall over that time period, what the predicted flow would have done and would have caused the flooding, and through the management of our system, what we're actually able to achieve here. So we want to get from there down to there by shifting this amount of volume at the right time. Timing is absolutely everything with this. If you don't know when a rainstorm is coming in, when those peak flows are going to hit the rain gauges, and when there is actually a risk of flood actually going to happen, all of your efforts can be at naught. And this is the problem with manual systems that have existed in the past. Yes, you can open and close sluice gates manually, but those are a very sort of a rough approximation as to what you think is going to happen. This is a precise science, and we'll show you the science behind what we have used in order to get that timing absolutely right. So the project that we've done is in two parts. First of all, we've actually developed a system which can predict flooding, and it can actually make those predictions within about 5 minutes. Now, this compares with existing systems that, say, the Environment Agency have, which could actually take hours to run, and they're expensive modelling systems. The success that we've had so far is pretty good in terms of accuracy. Where we've got a lot of data, we've actually had success rates of about 80% on average. But what this does mean is that a system like this can be used continually to better predict when flooding is actually coming in. Now, the other half of the system that we've got is all about optimization, and it's about water optimization for these upstream retention ponds. So imagine we've got our river, and there is a town downstream, and increasingly that town is becoming flooded. Infrastructure is being stopped, houses are being damaged, perhaps there isn't enough money to go out for grant flood in aid and actually get a big solution to this. What do people do? Now, if in this example there are farmers' fields upstream, then there is the opportunity to actually develop retention ponds where surplus water can be diverted into those ponds and stored until the problem has actually passed. Now, just one or two little ponds probably isn't going to work it. We're looking at increasingly changing the landscape of parts of our countryside so that this type of infrastructure, this type of networked infrastructure, can be developed so that they work in harness with each other. This is a big ask, because at the moment we don't actually have an industry which allows that to happen. We don't have distributed infrastructure developers who will go out there and do a little bit here and a little bit there. So one of the sort of themes I wanted to bring out today was actually how we need to change our industries and change how we innovate in order to make these types of solutions work. Getting back to the research project, you can see how we've actually managed to take a real live case. This was 2005. We used a lot of historic data from the Environment Agency and from the Met Office to look at what was happening every 15 minutes over a 20-year period. That's a lot of data, at a number of gauging stations, so that our system could then start to match patterns. Now, this is all to do with machine learning. It's basically a sort of a black box technology. You decide what you want to put into the black box, and you decide what comes out, and some magic happens in the middle. That's the limit of my expertise in this. But it means that if you've got that data, and really you need a minimum of 3 years data to make this work. If you've got that data and you can format that data so that it all fits into a common time framework, So we had to use special techniques to actually do that because we had multiple data sets. Then you can start training your system. You need to find special algorithms which allow that training to take place. This is not easy stuff. I call it black box technology, but it's actually not easy stuff to do. You've got to do a lot of trial and error, try lots of different sort of techniques. But for the period of research that we had, we actually came up with a solution which was getting these types of results. We also looked at how we could optimize a series of flood retention ponds. So we've actually got 3, 4 and 5 of the upstream retention ponds, and downstream is your village which is about to get flooded. Ignore 2, that's just there to make the system work. And the other technology that we've been using, which is called least means squared algorithms, optimization. It's a well-known technique. We spent 2.5 years actually developing this particular optimization. And now we can actually apply it along with our flood prediction so that all of the individual ponds, they can be drained down exactly at the right time and they can be allowed to fill up. If you're draining down a pond, you've got to make sure that you aren't actually going to flood the river in the meantime. So there are a lot of parameters in actually making a system like this work. What the system does is, first of all, has a best guess, and then it actually carries out its routines. And you can see how closely those routines actually match those best guesses. Now, I think the big question in our mind, having done this, because we actually felt very pleased with ourselves that we got this far with fairly limited resource to prove that you can have these synchronized upstream retention systems. You can have these distributed solutions which can actually provide a powerful tool for communities to build in more resilience into the systems that they've got, to actually give them more flexibility as to the way that they deal with these sorts of risks, to actually provide solutions which can deliver multiple benefits, and which actually provide a framework for other things to happen which will actually help in mitigate those overall risks. So, for example, let's say we've got our network of upstream retention ponds. Those ponds aren't going to deal with every single flood event. So if you actually get something which is on a biblical proportion, this isn't going to stop it, but it can actually be part of a hierarchy of solutions which kick in. We're particularly interested in trying to manage those smaller events which are becoming more frequent, that used to be maybe 1 in 50 are now becoming sort of 1 in 10 events, where you might get overtopping by maybe just 50, 100 millimeters on a local watercourse. But the impact that that actually has is significant for local economies. We were looking at the Embrook, which is down in Wokingham, and there's a particular roundabout there which actually regularly floods, and it causes a lot of problems to traffic, emergency services, local businesses. There is a value to it. So what happens when those retention ponds are no longer useful? They're overtopping themselves. We can then turn to other solutions, for example, actually using farmers' fields, so that the reservoirs, they can then overflow into fields. But what you then need is to actually have a system with insurers whereby those fields are actually going to be insured for loss to the farmers, or have a retention payment which is actually made to farmers for a certain number of periods. There are a lot of things that we can do when we think about distributed solutions. I think we so need to get away from the idea that infrastructure is all about building hard lumps of concrete and steel, no matter how smart they are. Nowadays, when we talk about distributed solutions, we're talking about services. A farmer being able to offer a service using some assets that he's got. Or it could be on the demand side, for example, incentivizing the customers of a water company to use less water by adjusting their bills. These kind of distributed water solutions will be very powerful if we can change our approach to the way that we go out and actually procure this type of work. And one of the other things that we're looking at the moment is how entities, so local stakeholders, can come together and actually collaborate. Now, you think, well, they're already collaborating. You're getting water companies talking to district councils, talking to farmers. Actually, our ability to do that is very limited. And it's very slow. And it certainly doesn't address the wider bag of water risks that communities are actually facing. So, if we actually want to take a holistic approach to water resource management, and we recognize that developing distributed solutions is the answer, and underpinning those distributed solutions, we need to have a systems approach. There's one more thing that's missing, and that is actually developing a form of marketplace whereby that collaboration can be brought together and these types of values can be brought out so that the investment is made into these types of solutions. Now, this is a big vision. This is something that ourselves, WSP, and some others are actually working on. And I think it's interesting coming along to these types of shows to actually see whether our type of thinking is being picked up by the wider industries at the moment. We're starting to see some signs, but these things actually happen sporadically. For example, you've all heard about blockchain, I assume. Blockchain, is the latest sexy thing within fintech. Everybody wants blockchain, they want Bitcoin, they want all of these sorts of things. IoT, have we heard about IoT, the Internet of Things? How can you actually start linking physical things together across networks so that they're all talking the same language? Smart sensors, satellite data, all of these things potentially are linked. Potentially, you can have a system whereby something happens within the environment. You get a low reading on water quality. You get a flood prediction. There's a potential shortage of water coming up. Rather than actually waiting for lots of different entities to come together to try and actually sort out the solution to that, in the future, and this is probably the scary bit, we actually have a world which is run by algorithms, whereby we actually have multiple systems which are actually talking to each other within predefined contract terms, which allows things to happen. So, something bad happens over here, upstream, a service kicks in and actually does something to actually mitigate that downstream risk, and that service provider is automatically paid. So you have this wonderful potential chaotic world where all of the old ways of taking 20 years to design and develop a reservoir are no longer relevant, where we actually have to have rapid, flexible, resilient solutions to things. So our little bit of work that we've been doing over the last year is just one very small part of this overall move towards a world of distributed solutions, a systems approach, connectivity, smart use of data, and actually breaking down the barriers between all of the different types of industries so that we can take a holistic approach to making our world a safer and better place for both humans and the natural environment. Thank you very much. I'm glad you're still here. And if anybody would like to ask a question, then I'm going to come around with a microphone. My hearing is rubbish, so I can hear you and you can talk into the microphone. I bet you are just bursting to ask a question. So who's going to be first? Let me come around to you. You'd like to say who you are and what your question is?
Yeah, I'm from Oxford. My name's Richard Frith, and we get floods there every 5 years or so. Abingdon Road underwater, etc. It's a big river system. It would be a huge amount of technology integration for your systems to be developed to actually have an impact on it. Is that something that you are looking at? A place like Oxford with the River Thames.
Thank you, Richard. No, we're not looking at Oxford at the moment. We are looking particularly down in the sort of southwest of London. We're also looking on the Crane catchment in West London and doing some things over in southeast London on Thamesmead. But we have looked at a number of catchments in the past. As I said earlier, if you have problems of a certain size, then what at best you're trying to do with systems like this is give yourself more time. You're not necessarily trying to stop all flooding, and that as a country is something that we have to get used to. So there are lots of other things and lots of other solutions in shows like this which will actually help with some of those problems. What our system does is to deal with particularly the low-level flooding, as I said, literally where you're overtopping by a small amount, and that happens more frequently. But also on the bigger events where you can actually start to buy yourself time so that other things then kick in. Now, if you wanted to scale up the solution, then the idea of being able to flood fields, use low-lying areas, a lot of the sort of natural systems thinking which is going on at the moment can be put into play. What we're trying to do is to find a smart way of actually synchronizing all of these efforts so you actually get maximum effect at the end of the day. Who would like to ask a question? Excellent. I'd like to say who you are.
Okay, my name is Kofi Todro. I'm from Scotland, local authority in Scotland. Anyway, I just want to know whether, when you say that you are limiting the controls at the upstream, whether your algorithms take into consideration the fact that rainfall patterns might differ from one part to the next. So, what if the heaviest rains are falling at lower levels while you're doing the controls at the upper end? Thank you.
No, that's a very good question. And one of the things that we've had to do is to find a technique for looking at the different patterns of precipitation across a catchment. And I won't go into the details of that, but what we do is actually work on a cell basis where we're dividing up an area into a grid effectively. And we're actually always looking at the relationship between precipitation across that grid as it actually affects the different rain gauges and then actually on the river gauges themselves. So, but using some clever maths, that is something that we do. So if you say, if all of the heavy rain, for example, is falling downstream and there's little to actually collect upstream, then there's no point in actually draining down your system. What you want the river to do, which is part of the system, you want the river to be using its full capacity to take on board that low-lying rainfall. Now, it's likely that that rainstorm is then going to shift. And so what you want to do is then start to find that window of opportunity to drain down your own retention ponds just in time to then capture that rain. So the stage that we're at with our development is that we've done less than a year's worth of development on this. We have early results which surprised us as to how good they actually are. We're now trying to talk to the Environment Agency to get their interest in this, and perhaps some other developers as well. Can I just ask, are there any environmental investors in the audience today who's brought money along? No. Okay, well, that's disappointing. But we would like to think that there is a willing industry out there which is looking for innovations like this, so that we can then take this to the next stage. Any more questions?
My name's Pete. I'm from a company called IoT Invent, so we look at sort of IoT solutions. You mentioned big data and IoT. I was just wondering, is the challenge getting the sensors out there to collect the data, or is it that the sensors are out there and there's all that data, but it's actually bringing it all together to be able to use it?
No, thanks very much. This whole area of data capture is so fundamentally important to everything that I've been talking about. And I was talking to somebody earlier who was wondering whether there would ever be a grid of smart sensors across the country. And my response was to that was that actually that's not the right way to do things. Physically, very difficult, very costly. One of the big areas of technological development at the moment is in satellite data. Now, we work with a company called Resitech down in the satellite catapults in Harwell, and they're experts in taking all types of satellite data and actually interpreting that for the use of the water industry particularly. And what we could potentially have in the future is, say, an IoT system which is actually being driven by satellite data which is being renewed on a regular basis. I mean, it's not going to be long before every square metre of the Earth is going to be passed over at least sort of once a day, and you can actually start to update those readings. But what you do need is to actually have those smart sensors on the ground in order to validate that satellite data. So the fact that the satellite sees something which is bright orange, it doesn't necessarily know what that means or what the health of that bright orange element is. So you need to get onto the ground and you need to validate things. So if you can actually have intermittent smart sensors across a catchment or at key places where you might be doing infrastructure type things, then that can work with the satellite data and you've actually got a more complete system. But to that, you also then add all of the historic data that you've got, and you're starting to create a very, very powerful set of data that you can then manipulate. Any more questions? We've got 20 seconds. Who would like to take a 20-second question? One quick question.
Whether you use, in this country we have radar station to monitor rainfall precipitation. Do you use them as well?
LiDAR. Yeah. So LiDAR is very important. making sure that we actually have the latest weather forecasts is very important, because that's not something that we do. What we're doing is actually taking the forecast data. The better and better that becomes, and it's improved enormously over the last few years, then the more accurate our flood predictions can actually be. So we are reliant on others, but in this country we've got a good system. Transporting the same technology overseas will be dependent on how those data systems are in other countries. So it will be useful to see whether things like satellite data can actually help to fill in where they don't perhaps have these types of radar systems actually on the ground. And I believe that's my time is up. Thank you very much, everybody, for coming along. I hope that was useful.